Okay guys, now that we've looked at the geometric model, where the goal is to play till you win one time, we're ready to move on to the binomial. Binomial is a little more complicated. First of all, you have two parameters, two things that are going to change from model to model. One is the number of trials you have, so the number of times you play the game, the number of times you flip the coin, the number of times you roll the die. That's always called N. P is still the probability of success. So that's the same as what we saw with the geometric model. Q is 1 minus P, so that's the probability of failure. Always should add up to 1. The biggie here is that we've changed what our random variable means. With the geometric model, the random variable was counting how many times we played, how many trials to get one success, the first success. Now that we have a distinct number of trials to start with, instead of counting trials, we're counting successes. So if we flip the coin 10 times, what's the probability of getting 6 heads? That would be the sort of situation we're looking at here. Most of the notation is the same, probability that the random variable number of successes is equal to a particular number, but the formula looks quite different. We're still going to multiply a number of successes and a number of failures together, but now we've introduced this new little component right here. This is that combination of n objects taken x at a time. So if we flip 10 times and we want 6 heads, this is going to count all the different ways that can happen. So we can have heads, tails, heads, tails, heads, 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 tails, tails. Or we could have heads, tails, heads, tails, heads, tails, heads, 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 heads. So there's all these different ways that you can get the outcomes. Order doesn't matter anymore. So this is your counter that counts how many ways you can get those orders before we multiply by the probabilities, so that we don't have to sum a whole bunch of different possibilities. That's an endlessly long list that's really hard to make. There's also a mean and a standard deviation formula here. These actually do pop up on the AP exam. All 3 of these formulas are in your blue book on that second page where your probability formulas start. They're in that second set of probability formulas, all 3 of those, and it actually does say in that blue book that these are for a binomial distribution. So it's spelled out, just black and white, what those are for. These will not go away. We will have to know those. Okay, so let's work some problems. We want to know the probability that we'll find 2 candies, 2 speckled ones, and a handful of 5. So we're still pulling from that big bag of M&Ms we looked at before. So we have speckled and not speckled. We remember that the probability of a speckled one is 30% and the probability of a not speckled one is 70%. And that it's a big enough bag that if we pull out 5 candies, it doesn't change the probabilities enough to make a difference. So we're going to pretend that things are independent because it's close enough that we can just let that be. That 10% condition will override. Okay, so I want the probability that out of 5 candies, that would be our n, so n equals 5, out of 5 trials, we're going to find exactly 2 speckled ones. So probability that the number of successes, that's capital X, is equal to 2. So we'll read this, probability that the number of speckled ones is 2. Now to get that, we need to find all the different ways to get 2 speckled candies in 5. So we could get speckled, speckled, not, speckled, not, speckled, not, speckled, speckled, not, speckled, not. There's all these different combinations, not, speckled, speckled. And each of those we have to calculate probabilities for and add them all together. So the quick way to do that is to do a combination. So we have 5 candies. We're going to take 2 at a time. And if we do the combination of 5 candies 2 at a time, this combination will calculate all the different ways that we can pick 5 candies with 2 of them being speckled. Then we're going to multiply by the probabilities. So the probability of speckled, that's 0.3. We'll have 2 of those. So 0.3 times 0.3, that's 0.3 squared. And then there will be 3 non-speckled ones. So 0.7 times 0.7 times 0.7, so 3 of those, so 0.7 to the third. So these powers are always going to add up to 1, or sorry, add up to your n. So 2 failures and 3 successes, or 2 successes, 3 failures adds up to 5 total trials. This finds the probability of getting that happening one time, and then we multiply it by all the different kinds of ways it can happen, and then that gives you the probability of all the different possibilities. Now, we have to get that in the calculator. So, want to be on a calculator page, menu, probability, and combinations, number 3. And we're going to do combination of 5 objects, taken 2 at a time, close our parentheses, times 0.3 squared, 2 successes, times 0.7 to the third, so 3 failures, and that's equal to 0.3087, so almost a 31% chance of that happening. Now if we kind of link it back to this formula here, let's make some connections. So here's your combination, 5 choose 2, probability of success, that was 30%, how many successes, that's 2 of those, that's your power, and then probability of failure, that's Q, and then 5 minus 2, or third power for that one. So this is a direct application of that formula. Alright, now that we've seen the first one, let's take a look at another example. So more speckled M&Ms. What's the probability that we'll find at least 2 speckled ones in a handful of 5? Okay, so that means we could find 2 or 3 or 4 or 5. Now, the long way, P is probability of X could be 2, or X could be 3, or X could be 4, or X could be 5. Or we could write the probability that X is greater than or equal to 2. And that would get the job done just as quickly as this. It's just a little easier to look at all the different possibilities. But this notation is, it's more efficient. We know that we start at 2, we can go up to 5, and 5 is the limit that we can reach in this problem. So let's see what happens with 2. So if we can have 2 speckled candies, then that means there's 5 candies, 2 of which are speckled, and that success is 0.3 2 times, and failures 0.7 the other 3 possibilities, so 0.3 squared and 0.7 cubed, which is the same thing we just computed on the other page. But now we have to do OR, so recalculate for X equals 3. So we have 5 candies and 3 could be speckled. So how many combinations are possible there? Times 0.3 to the third, 3 successes, times 0.7 squared, 2 failures, for a total of 5 trials, plus X could be 4. 5 candies possible, 4 of them are speckled. 0.3 is successes, there's 4 of those. 0.7 failures, there's only 1 of those. And last but not least, if we get 5 candies, that's 5 candies, all 5 are speckled. Technically that's equal to 1. Calculator will know that. And then 0.3 to the 5th, 0.7 to the 0, which is just 1, so we can leave that one off. Now, this one's going to take some time to key into the calculator because you have to do combination, multiply, combination, multiply. This is quite a bit of work. So wouldn't it be just handy if there was a shortcut? Well, of course there's a shortcut because these calculators are amazing little creatures. So I'm going to go to the menu and see if I can find something useful. Probability might be useful since I'm calculating a probability. Distributions, number 5 is where all my special stuff is stored. And if I look way down at the bottom, I see something called Binomial PDF. Let's check that out. If we just press A, then the Binomial PDF menu will pop up. Now, Binomial PDF will tell me the probability for 1 point, 1 value. So that's kind of like the last problem that we did, where we had 5 trials, 5 candies are getting picked. The probability of success was 0.3, and the X value, which was how many candies, how many successes, how many candies are speckled, was 2, and that was the 0.3087 that we got the long way. So we have a shortcut, but that's not this problem. That's not the one we want. Let's go to this problem. Let's go back to menu, probability 5, distributions number 5. Now there's more stuff down past Binomial PDF because there's an arrow there. The next option is binomial CDF, and CDF is a cumulative density function, which means it accumulates for more than one x value. That's the one that we need. So we're going to go with choice B. And this time we get a couple of extra options. We still need number of trials, 5. Probability of success is still 30%. The lower bound is the least number of successes. So that's the least number of speckled ones. We want at least 2 speckled. And the upper bound is the most speckled. So the most we could get is 5. So this is going to give us everything from x equals 2 to x equals 5 inclusive. So it'll do 2, 3, 4, 5 all in one fell swoop. And we click on OK. And this is the probability that calculates all this crazy business right here without having to actually key all of that individual stuff in. It's beautiful. It's a great, great thing. So this is equal to 0.47178. I'd probably round to like 472 if I were doing this on a test. Alright, let's try the next one. You pour 10 candies out of the bag. What is the mean and standard deviation? Oh, we poured 10 out, that's n, of the number of speckled ones. The number speckled is the number of successes. Oh, this is binomial because we have a predetermined 10 and the probability of success is 30%. Alright, so I have formulas. I have a formula for a mean of x, which is number of speckled. The average number of speckled is n, that's how many trials, that's 10 candies, multiplied by the probability of success, which is 30%, which is 3 candies. Okay, does this make sense? If 30% of the candies are speckled, if we pull 10 out of the bag, 3 of them should, in a perfect world, be speckled on average. That's 30%. That makes sense. Okay, the standard deviation formula says take the square root of n, that's 10, times p, probability of success, that's 0.3, times q, the probability of failure, that's 0.7. Alright, that's something that would be a nice problem for the calculator. So square root of 10 times 0.3 times 0.7 is 1.45-ish or 1.449-ish, depending on how you want to round that. We'll just do 1.449-ish. So average 3 M&Ms with a standard deviation of almost 1.5 M&Ms if we pick 10. Alright, the next little series of questions are all kind of the same scenario of an Olympic archer. So I'm going to have to stop this video and we'll restart a new round to get this last little chunk of problems. So you'll have to go on to video number 2 to finish up the notes.